So, what is the idea of champions lists? The idea of champions lists, and that is where the engineers enter the picture, is the following. There are some, I mean, we may have a lot of memory. Actually, probably we have. If we are running a commercial search engine, we have a lot of resources available. The point is that some operations are a bottleneck. So computing all these cosine similarities for every document is a bottleneck. I mean, you may have as many machines as you want, but that's a computation you have to do. So can we increase the amount of memory we are using so that we can try to speed up the computation of perhaps not top K, but very good K results for a given query? What I can do is the following. I could, for example, decide the following. I pick a value, R. So let's say, what are the inputs to my problem as an engineer now? The input to my problem is essentially K. Of course, the posting list and all the rest, but essentially it is K. So the amount, the number of high-ranking K documents for which I want to compute. Okay. What could I do? Well, I could say the following. I pick some value R that in general will be larger than K in general. Actually, it will have to be at least K. And then what I do is that for every term in the dictionary, so every term, I pre-compute the top R documents for the term. You see this? Essentially, it means that for every term, we are going to pre-compute the R documents in which the term appears more frequently. That's relatively easy to do. And you do it once. You do it once you build the index. It is clear that whenever you add a new document to the collection, you have to update the index, right? So you will have to update the postings list and so on. And you will also have to decide whether or not, for every term, this document appears in the top R or not. Is that clear? It's simple. I just compute the frequency of the term in that document. And I see whether or not it is one of the top R scoring documents for the term. So I will have what is called the champion list. So you will have so this is your index of the terms. Then for every index you have the standard posting list. Plus you have a champion list. The difference is that the champion list contains only R documents. And these are the top R documents for this term. Okay? Now, how am I going to proceed? Whenever I want to compute to return results for a query, I will just run the algorithm we have seen before, but on the champion lists instead of the posting list. Okay? And eventually I get a collection of documents. So notice that I do the very same thing. So I pick the top K documents, but it is as if I were working with this posting list and not with this other posting list. Of course, what can happen? Well, if I don't pick R large enough, it could happen that, at least for some queries, I get less than K documents, right? Well, if that happens, I have to integrate with other documents coming from the original posting lists, okay? But let's say that if I pick R large enough, most likely I will always be able to satisfy the query. I mean, most of the times I will be able to satisfy the query by accessing the champion lists, okay? So what can I say? Can I give a proof that actually the top K documents I return based on the champion list are related to the true top documents? No, I'm not going to do that. I do a study. I do an experiment, and I check how well it's going to perform. And apparently, it is normally going to perform pretty well. Okay? Of course, the value of R has to be chosen with some care. In particular, it is one of those cases in which you have a trade-off, of course. The larger R, the better. The chance of not being able to return K documents decreases. On the other hand, the less useful it is to have a champion list if R is very large. So you have to trade off. How are you working? You do an experimental study. You submit, I don't know, 1,000, 10,000 random queries. I mean, perhaps not quite random. Typical queries, most frequent queries. And you check how your system is going to perform with a given value of R. And you tune R in this way. Okay? So, and this is a pretty engineering approach. Okay? They don't knock at my door for this type of things. For this type of things, they really need intelligent people that are able to solve real problems. How can champion lists be implemented in an inverted index? Okay. Is this a real picture? I don't know. I should ask a real search engine. But let's say, logically, yes, this is a picture. In practice, they might keep these into separate areas of memory. This is, for example, an ultra-fast memory and this not. Okay, I mean, there is a number of ways to do this. Posting lists residing on disk. Yes, once at least part of them was residing on disk. Now, they using compression and so using large memory machines. Now, using tiering, we will see what tiering is. Actually, very often you have posting list in main memory. Okay, perhaps not the entire index. The index is split into sub-indices, and everything is in main memory. Okay, and then perhaps you have another machine that is dedicated to champion lists, and so on. I mean, there is a number of ways in which you can implement this. If you ask me which is the correct one, I have not enough information to provide an answer. I should be there operating. For example, another issue, what happens when you want to do index elimination? Well, you just don't consider some of the champion lists. Simple. Either tout court, which means, for example, if I have very frequent words such as to, I'm not going to have a champion list for to. Perhaps I remove to from the query. Okay, so yes, index elimination and champion lists can be put to work together if you want. Then let's come to another point. So far so good. Champion lists seem to provide an engineering principled way of approaching the problem of computing all those scopes in similarity scores. Can we expand this idea further? Well, yes, we can, but in order to do that, a new element has to enter the picture. So the fact that very often as I was telling you at the onset of this lecture, very often you have a combination of, so the score of a document for a given query is a combination of two elements. One depends on the contents of the document with respect to the query. And that is something you compute at query time. I mean, there is no other way. Then there is another part of the score which does not really relate to relevance with respect to the query, but is query independent. Okay, that's very important. So very often your score will be
Your score will be a function of a global quantity that depends on the documents and not on the queries. Okay? And which in a sense measure authoritativeness of the documents. So how authoritative the document is on the basis of some general criteria. And instead, a score, which actually I should have, that is query dependent, and for example is the relevance computed, estimated, measured by cosine similarity. Okay? So you have two elements. And the final score will be a function of these two elements. Okay? So the important point here is that this one is not query dependent. It is something that you compute once and for all on the document collection. Okay? Is it clear? So, one such measure, of course, is the famous or infamous PageRank. There is something we will see. To compute PageRank, you do not need information about pages. You need information about their hyperlinks. That's all. And it's query independent. But there are other ways of measuring the authoritativeness of a page. For example, there are some repositories of authoritative web pages for given topics. You could just take that information and plug it into your scoring. Yeah, you can do that. If you're considering papers, you could consider not PageRank, but just the number of citations. So that's actually what they do to measure impact in our system. And the results are not outstanding, I have to say. Let's say perhaps PageRank would be a better measure, but there is a problem of having our ministry understand what PageRank is. Let's put it this way. Anyway, there is a number of independent measures. So, once this is clear, perhaps we can try to integrate this information within this general idea of having contender lists. Okay? Something like champions lists. One question. Oh, there is an exercise. This is nice. Let's say the following. I want to measure the authoritativeness of the papers by just measuring by using the citations. You know, the more cited the paper, the more important the paper. Can you give me an idea of how I get a score between 0 and 1 for every paper? Is it clear, the question? I want to give every paper an authority score. It should be something between 0 and 1. And I would like this quantity to depend on the number of citations of the paper. So the more cited the paper, the more authoritative the paper. What is a good choice? I mean, the first choice that occurs to you? Oh, you can just take the in degree of each node. Each node corresponds to a paper. Every link is a citation, so this paper is citing this paper. And you normalize by the total number of arcs. Each paper will get a score between 0 and 1, and the scores will sum to 1 by definition, right? That's a way of measuring impact. Actually, this is the way impact factor is computed. Alternatively, you could do something else. For example, you could compute the PageRank of this network. Actually, I think that measure is much more suitable to rank papers, but this is an alternative one. Okay? So, what is the net score? What does it mean? The overall score, what I was calling f, the function f. The net score is a combination of the query-independent score and the query-dependent one. How do you put them together? This is a nice question. So, stupid way. GD is something between 0 and 1. Cosine, something between -1 and 1. In principle, you sum them. You take them and sum them. Okay? Is this working or not? I don't know. What is specific about this choice? First, you are just adding them up, which means you are taking a linear combination of them. Is the linear combination the best choice? Who knows? Perhaps, perhaps not. Right? Also, if you provide a linear combination, why not something like this, where, for example, why don't you take a convex combination? Why this idea? Because perhaps the quality of the results you provide to a user is maximized not when alpha and beta are the same, but when alpha and beta are slightly different, according to some ratio, for example. For example, you may want to give more information to the static part. So if a page is authoritative, you may weight it a bit more. So contributing to the global score can be done by setting alpha equal beta, which is the initial formula, which is that formula. But actually, any combination of alpha and beta might work. Any convex combination. You don't need to take alpha and beta arbitrary. They can always sum up to 1 in case you normalize, right? So what is the best choice of alpha and beta, for example? Boh. In Italian, the answer is boh. So unless you have further information, the answer is I don't know. And how can you measure this? Also, how can you pick the best choice? That's a very interesting research issue, because actually it has a name. It is called learning to rank. So if you want, this is a learning problem. How? Assume that you have a training collection, right? You have a training collection, and which means a collection of documents, and a collection of queries. And for these documents and query collection, you have the best rankings decided by humans. So how does this, in some conferences there are standard dataset collections that are used to perform this task, so to measure how algorithms are going to perform. In that case, for example, the TREC, TREC collection is very famous and widely used. How does it work? You have a document collection, you have a query set, standard, and essentially for every query and the document collection, you have the top K documents. But in this case, the ranking has been decided by human judges. Okay? So let's say 3, 5 people, 10 people have just each decided which was the best ranking, and then some voting scheme was applied that maximized agreement between the judges, and that is taken as the ground truth. The idea underlying this is normally that the best judges are actually humans, not machines, because they have much more flexibility than machines. And that is normally what you refer to as the ground truth. Okay? So that is taken by the truth. I'm not claiming this is the truth. I'm just saying this is the ground truth, with respect to which you measure the performance of the algorithms. Then what do you have? You have a formula like this. And you can apply the formula to run the very same set of documents with respect to the queries in the data set, in the training set, with different values of alpha and beta, with different combinations of alpha and beta. And depending on the values of alpha and beta that you choose, your rankings will agree with the ground truth more or less, right? Now, we are not discussing how we measure agreement of two rankings. We will see that. Is it clear what I'm saying? Yeah? So you can perform better or worse depending on how you pick alpha and beta. Okay? So you will try, what you're going to try is to solve an optimization problem. And the optimization problem is the following. Pick the best value of the values of alpha and beta that will maximize some function of the agreement between the ranking decided, the ranking returned for every query on the document collection and the true and the ground truth for the document collection. Okay? I mean, we can write the optimization problem for some example. I'm not doing it now, but just be aware that it is possible to define it in some way. Okay? Because you have the ground truth, so you know what the answer should be. You can measure you can measure how the ranking provided by applying this formula for a given value of alpha and beta differs from the true ranking. There are a number of functions to measure this, and at that point, you have an optimization problem. You want to minimize the disagreement, so the Euclidean distance, the number of inversions between your ranking and the true ranking, using alpha and beta as variables. It is called, it's a learning problem. It's a machine learning problem. And actually it's called learning to rank, okay? So that is actually what search engines do. So the values of alpha and beta actually are not just computed by hand. That's the old way of proceeding. Now you do actually something different. On top of that, maybe we're using a linear combination, maybe not. Maybe we are using a nonlinear function, okay? Why? Let's say that some aspects of human thinking are apparently better captured by nonlinear functions at some points, at certain points, okay? So maybe we are not even using a function like this, we're using a more complicated function that perhaps nonlinearly depends on the results, the outcomes of previous iterations and so on. But in a nutshell, what we are doing normally is choosing some form for this function and then optimizing its parameters with respect to the training set. Okay? That is how you do this. Is that clear? It is a high level for the moment. So, why are we introducing this? Because at this point, let's assume for the moment that we have a linear combination, or simply the sum, okay, just for the sake of simplicity. In general, it is intuitive that the higher the authority, let's put it this way, the higher the score should be, more or less. This part of the score, at least. So, can I leverage this fact, so that the fact that when I am going to compute the score for a document anyway, I have to take a function that also depends on something static, regardless of the query. A reasonable idea is, for example, to do the following. Why don't I simply define champion lists with respect to GD? Why? Well, this is easy to do, right? You just have to rank, you provide your champion lists of the first R documents according to decreasing values of GD. That's simple to do. You have to compute this anyway, and once you have it, you can compute the champion lists immediately, right? So, actually, you can do even more. You could do the following, but look, since in the end I had to compute the document, I have to compute cosine similarities and then sum them with the static score. I mean, I had to sort the documents. Well, you know, when you apply the, let's say, merge algorithm, it is important that all the documents are sorted in a common way. Normally, documents are sorted by doc ID, just because that's a common criterion. But now, maybe we have another common criterion, because the very moment I apply to every document a static score, I can define an ordering with respect to the score, right? Do you see what I mean? Huh? Hey, are you getting me? Where is the advantage? So if posting lists are sorted according to decreasing values of GD instead of according to doc ID, the documents, the posting lists are still sorted in a consistent way, right? Which is okay, I want that. But at the same time, the top ranking documents according to GD appear in the first positions. You see that? And that could be an advantage, right? Why? Because intuitive, in many cases, let's say the top ranking documents for a given term are more likely to appear in the first positions now, just because this part of the score is higher. You see my point? I mean, it's not necessarily like this. Perhaps you have a document that has a very low, let's say, absolute score, static score, but very high relevance for the query. Then this document might be deep in the posting list, right? But such a document, what can we say about such a document? So a document with a very low value of static score and a very high value of relevance. What can we say? What do you think? Like fake news? Yeah, without arriving at fake news, yes. I mean, perhaps spam or, you know, could be relevant just because perhaps I've been repeating game 1 million times. Okay? So, let's put it this way. Having a high static score but very low relevance maybe is not so good because perhaps I return a document that is authoritative but has nothing to do with the query. On the other hand, low static score, very low static score, and high relevance also. Maybe it's not so good, perhaps spam. Of course, there is a gray area in between, but it means that perhaps I do not have to search the entire posting list before I find relevant and authoritative documents for a given term, right? Okay, so I can stop earlier. So what you can do is the following. You sort posting lists by decreasing static scores, and you apply the idea of champions list. So essentially, you will scan the posting list, but stopping when you have reached when you have reached, let's say, R documents in every posting list. Okay, that's the end of your posting list. And then you check, do I have at least K results or not? If you have K results, you are done. You just compute, if you have at least K results, you compute the top Ks, and then you return your results. If you are not done, because you have less than K results, you can proceed a bit further, on the fly. So that's the idea of how you integrate champion lists with static scores. You see, again, this is not, how should I say, I mean, this is an intuitively motivated heuristic. I mean, there is no deep theory behind. It's just more or less common sense engineering applied, and the fact that apparently some of these ideas seem to work in practice. Otherwise, we would not be discussing them right now. Okay, I'm just discussing them because apparently they seem to work. Okay. Yeah. Let's say why 50 milliseconds if you want to be 500 milliseconds overall, let's say 50 milliseconds for this part. Then remember you have to build your result list and all that stuff. That's why you have to be fast here. So again, no, this is a different idea. The idea I just showed you was I sort posting lists by decreasing GDs. Okay, I'm not keeping extra champions list in principle. I'm just keeping, and then what I do is just I traverse them downward and I stop at some point. And I hope that the documents that I'm taking into consideration are containing most of the top K ones. That's different. This is another idea. I still have GD ordering, but on top of that, For every term, I'm maintaining also a champion list containing R documents for every term. And in that case, it will be the documents that have the highest global score for that term. Okay, that's the difference. So here, instead of Q, you have a T. You have a term. Is it clear? In every champion list, they will be sorted by decreasing. Okay. And then you seek the top documents for only these documents in a champion list. If you don't succeed, go back to posting list. I mean, if you don't succeed means if you get less than K documents. Or these are all variants of the same idea, more or less. So, and actually this what I was telling you now. But in this case, I will have a picture to show. So, essentially, you keep a high and low list. So high, let's say, contains, for example, those candidates. The low is a standard posting list. And you first try with the high list. If you fail, proceed to get documents from the low list. But, of course, there is an issue here. Why? If the two lists, the champion list and the low list, contain overlapping documents, you are wasting work, right? So you are going over the same documents again. So you will keep a partition. So you will tier your index. You will have two tiers for your index, one containing the top, the high posting list, and another one containing the low posting list. Let's see if there is a picture here. Where was it? There was a picture, I swear. Ah, here. Forget about this tier now. So the higher tier could be, yes, they should not be intersecting. Yes, they're not, I think. No. Let's say a high tier and a low tier. So the high tier will contain, for example, top documents sorted according to decreasing order or this. So you try those first. If you fail, you try to integrate. So why do you fail? Because, for example, you find if it is best car insurance, you will just fail because you will not have anything, any document containing best, right? So you retrieve two documents. You retrieve actually doc 1 and doc 3. No, sorry, not doc 1. You retrieve doc 3 from the first two posting list, right? But you're missing any document containing best. Where do you fetch it? Well, actually, you can fetch it from here. So you go down to the low posting list that contain many more documents. It's not like in this picture, so you should think in this picture for the sake of proportion. This should be very long Q posting list with respect to the first one, okay? But in that case, the missing document, the missing information that you have to integrate to get at least K results, you will get it from by adding documents from the low list, okay? That's the idea. And this is an example of index steering. So you, for example, you have two machines, one dedicated to the high posting list, the other dedicated to the low posting list, okay? Maybe a small fast machine for high ones, a fast, bigger one for low ones. That's what's up. So, we are almost there, actually. I still have some time. Okay. Oh, then there is another final idea, which actually goes hand in hand with this. So, so you got the idea of, let's say, champion list in its variants, right? So the basic idea is simple. So the idea of champion list still is consistent with an ordering of the posting list, which is in which every posting list is sorted according to the same criterion, doc ID or static score, right? So it means that the relative order of documents within each posting list is the same, okay? That's important because in principle it means that we can do some apply some parallel algorithm to merge, to compute the scores, okay? You see that? So you remember the basic merge algorithm, which can be performed in parallel, it requires a common ordering of the documents. Otherwise, it will not work. It cannot be applied because it's a merge in the end. The merge requires a common ordering. Okay? Now, on the other hand, if we go back, really back to this algorithm is working with one posting list at a time. So the outer cycle is on the terms, right? So this algorithm is processing one term at a time, which means one posting list at a time. It is sequential with respect to the posting lists. So this is called actually term at a time processing. Actually, it defines one of the two possible ways in which the scores of documents can be computed or accumulated, how the people say. One way is one query term at a time, which means one posting list at a time. If we are going for this way, then you can consider, you know, how should I say, the ordering of the posting list is no longer important. Why? Because anyway, you're not proceeding in parallel. You are not doing a parallel merge. You are processing one posting list after the other. So if they are ordered in a different way, what's the point? I mean, it's not really important. You are not exploiting the same ordering anyway. You see my point? No? Let me show you. So look at this algorithm. Where am I using the common ordering of the documents within each posting list in this algorithm? Am I using it somewhere? For example, am I using anywhere in this algorithm the fact that, for example, every posting list is ordered in increasing doc ID, by increasing doc ID, or by increasing static score? Am I using, or decreasing static score? Am I using this anywhere? I don't think so. I'm just scanning one posting list. Whenever I have an entry, it means I have a document, and I update the corresponding score. That's it, right? But whether or not these documents are sorted in the posting list for this term by doc ID, static score, or any other criterion, I don't care. I'm just scanning the posting list. Why? Because this is a sequential scan. One posting list at a time. If I wanted to do a parallel scan, I would need the same ordering within each posting list because I'm implementing a variant of the merge algorithm. But I'm not implementing a merge algorithm here. I'm just scanning them sequentially. Okay, so how documents are sorted within each posting list is immaterial. I don't care. Okay? Of course it works if you have a common ordering, but it's not necessary. Why am I saying this? Because the very moment you're not going to use a common ordering of the documents within each posting list, well, maybe you can do without and gain some more flexibility somewhere else. Okay? For example, what can you do? You can do what is called impact ordering. For example, if I'm using that type of approach, which is called term at a time scoring, what I can do is just sort every posting list of every term locally just by decreasing weight of the document with respect to the term. Okay? So since the weight of a document with respect to a term can change from document to document, right? So I mean the weight of a term for a document or of a document for a term can be different from document to document. Yeah? Document appears 10 times in a document, 100 times in the other document. So the weight is higher for the second document, right? So every sorting, every posting list will be sorted in a different way. You see? No? Who is lost? Come on, take your courage and tell me I'm lost here because of. Come on, tell me. Where did I fail you? What is unclear? Come on, it's okay, it's not the exam. You can honestly say whatever is not clear to you. Don't feel stupid. I mean, I had to go over this stuff thousands of times before I got an inch of it. It's normal. It's the first time. So what is the... Can one say, no, I didn't get this? I will be happy. Let's step back. Do you agree that the algorithm we have seen before is not using the ordering, the common ordering of the posting list? Yes. So if we order each posting list according to a different criterion, the algorithm is still going to work, right? Because it doesn't use the ordering. Correct? Am I correct? Good. Now, let's use this flexibility. Since we have it, let's use it. One way is the following. Since every posting list describes one term, so describe all the documents that contain the term, I can just do the following. I can order this posting list according to the number of occurrences of this term within each document. For example, this first document, let's call it D1, will contain the term 1 100 times. Then there is D10 that contains this document 95 times, and so on. Documents 2 to 9 do not contain the term. Okay? I can do this, right? So what is the advantage now? The advantage is when I run that algorithm for each term, the most important documents for each term will appear in the first positions. So I can apply the same idea over and over again. Okay? Since the most important term to compute the, let's say, the relevance part of the score appear first, maybe I can stop earlier. I do not have to go down the entire posting list. Okay? I mean, I'm not using the ordering, the common ordering. Okay, let's try to take the maximum advantage out of this disadvantage. Okay? So, how can I leverage this idea? The first way in which I can leverage this idea is just what I was saying. Instead of going down the entire posting list, for every, remember, for example, take the query, so the query has to contain the first two terms, okay, T1 and T2. So I will have to traverse these two posting lists, okay? You see? If I were proceeding in parallel, I would need a common ordering of these two posting lists. But I'm not proceeding in parallel. First, I will go over this posting list, and I will compute the contribution to the cosine similarity for this term. And then I will do the same for this second posting list. Okay? So, which are the most relevant documents for the first term? These ones, if they are downsorted by decreasing weight. So I consider them first, and I stop when I have seen, let's say, R of these documents. Then I do the following. I go down and I do the same for the second term, and I stop when I've seen R documents. Then, of course, once I have this collection of documents, I treat this as two posting lists with R documents each. And I do the standard, and I run the standard algorithm. What can happen? It can happen that R is so small that I will not have K documents. Huh? Well, in this case, I will have to go a little bit further. So you should notice, anyway, that I can do this while I am running the algorithm before. So I do not have to compute the first R documents, apply the algorithm, and then see if I have top K documents, K results at least. I can just run the algorithm, and on the fly, I can check whether I have collected enough documents, right? Huh? When the score vector has a length which is K or larger, I am done. You see my point? Huh? Okay, I can do this on the fly. So I would like you to think about at home, okay, how you can implement this on the fly. Okay? But in order to do this, every posting list will have a different ordering. But it's fine, since we are not using a common ordering. Another idea I can apply is the following. It's a different ordering. I'm still in this case, I'm looking at the terms that appear in the query. And I do the following. This applies especially when you have long queries. If you have two terms, it's not really going to be very useful. But let's say if you have 10 terms, you can consider sort the terms in the query by inverse document frequency, and then consider them in decreasing order of index document frequency. And then essentially, you start extracting documents, the most relevant documents to this posting list until you reach K documents, and perhaps you stop before you had to consider all the posting list of all the terms. Okay? That's called, again, early termination. I mean, in the first case, we were considering all the terms, but we were terminating earlier, in the sense that we were not visiting all the posting lists. In this case, we are maybe visiting every posting every posting. So one posting list entirely, but we are not visiting all posting lists. Okay? There is always this dual approach, documents versus queries. Let's say that most often you go for documents, because as I was saying, most of the queries have very few terms. And then, I think for today, I still have time to just give you an idea, an outline of this idea. We'll take it from here next time. What is called cluster pruning, another way to speed up things. Again, this is engineering with some theoretical intuition behind. There is always some theoretical intuition behind. And it is called cluster pruning. What does it mean, cluster pruning? So again, we want to limit the number of cosine computations that we have to do. Okay? Very clear. And we do the following. We leverage the vector space model. So what is a point? Sorry, what is a document here? I mean, what is a document? This is a document, right? It is a point in a high-dimensional space. Documents are this. That's a document collection. So why am I drawing here in this way? Now, there is always the issue when you have many dimensions that we are humans and we only see two. We plot 2 dimensions and we see 3, right? That's a problem. when we have holography all around, we will be able to also draw 3 dimensions. But for the moment, we mostly draw 2 dimensions. Now, what happens is that if cosine similarity is capturing distances, and in this case, we think of these points as normalized, so they are actually on the unit sphere. Distance and cosine distance and Euclidean distance are the same thing. Huh? And actually, you may notice, if you are able to look at these points in multiple dimensions, in hyperspace, you would perhaps see some form of clustering. So, what does it mean? That some documents are similar to each other. They more or less talk about the same things. Okay? And visually, they will appear closer to each other than the rest of the points. This is called clustering. Now, what does it mean? Because clustering has some nice implications. It means that, for example, if instead of considering all documents here, I just pick a sample, let's say this, in this case I'm being very lucky, this and say this, if I were able to sample these documents, and I were supposed to answer a query here, let's say this is a query point, what could I do? I look at the space and I see, what is the closest center? Let's say it is this one. Okay? I'm not sure it is that one, but let's assume it is this one. And then I will say, okay, this is the closest point. Since we are in a unit norm, this Euclidean distance, which is this segment, and cosine similarity will give me the same information. So actually, this is the closest, let's call these centroids. Centroids of the cluster, or actually they're called here leaders. Let's call them leaders. So the closest leader is a document that probably is relevant to this query. And if I want to enrich it with other similar documents so that I return top K, some K similar documents, what can I do? Well, actually, I can take documents that are closest to this point, and which I call followers. Okay? And the moment I have K of such documents, I will return the answer. Is this the best answer? Real top K for this query? Maybe not. But probably it's a good answer. Okay? This is called cluster pruning. What is the idea? The idea is that you consider only a subset. Yes?
And you can organize the document inside the...
In clusters?
No, the clusters, no, I mean, once that the cluster are formatted, are closed, we can...
So how can you organize it means which are the followers of a given leader, or?
Quello che voglio dire, posso dire, una volta che abbiamo i cluster, la query...
I said, no, in this case we have no clusters. I mean, I use the idea of cluster to give you an idea of, to tell you what is the idea behind using leaders and followers. Okay, the idea is that very often you have some clustering in the documents, so the points are not uniform. I mean, they can, but normally they are not. And the idea is that if you could guess, let's say, the centroids of those clusters, you would have a very nice way of answering queries efficiently. Because what you would do would just match in the query to the cluster centers, to the centroids, what are called leaders there. And instead of having to take n cosine similarities, where n is the number of documents, you would take a number of cosine similarities equal to the number of leaders, right? That's the idea. But I'm not saying that we are going to cluster documents yet. We could, actually, people do cluster documents, but that's not the idea in this case. The idea in this case is a bit simpler. It says the following. Let's pick, in this case, it is square root of n, leaders, uniformly at random, okay? So we pick square root of n points, where n is the total number of points. We pick them at random. and we call them the leaders. And then we apply the strategy I was telling you. Okay? So what is the difference between doing this and doing what I told you? The difference is that in this case with my human eye, I was able to find points that are representative of each cluster. If I just sample them at random, what is going to happen? It is going to happen that if I have a good clustering, so the documents are really clustered, and I pick square root of n. Square root of n is not a random number. It has a reason. If I put square root of n numbers uniformly at random, I have a decent probability of picking, let's say, some points within each of these clusters. Okay? Let's say that in each of these clusters, with a decent probability, that there will be at least one representative leader. If I have no clustering, doing this will be more or less useless. Okay? But the idea, if there is some clustering, which I cannot know in advance, with square root of n randomly chosen leaders, I may be able to pick representative in every cluster. Okay? And at that point, this idea may work. That is the idea. So how do I organize the data at that point? What I will do is I still have my index, posting list, and so on. But together with this, I will have some reference documents, which will be the leaders. And whenever I need to decide to return a subset of k documents for one query, I will just take the cosine similarity, sorry, between the query and the leaders. Okay? Once I have, let's see if I have a picture. Okay. Once I have computed the cosine similarity with the leaders, with all the leaders, I decide that I'm going to answer using the closest leaders. Okay? What is going to happen at that point? Consider that leader, I will collect the first k documents that are closest to the leader, and I will return that as the result set. Okay? So, what do I need to do to implement this algorithm offline? I need to do two things. First of all, I need to sample k documents uniformly at random, which are the leaders. And then for every other document, I will have to decide to which leader each document associates. And the rule is normally the following. Every document is associated to the closest leader. Okay? You see my point? So, why did the people who designed these slides provide this picture? Because that's the idea I was telling you about. So this old stuff makes sense if there is some clustering in the data set. If there is some clustering in the data set, picking square root of n leaders will give me, first of all, a decent probability of picking at least one leader in every cluster. And secondly, I will have cluster. So whenever you match a query to the closest leader, and you are returning a subset of that leader's followers, and probably their point that are closest to that point, and probably also close to the query point. Okay? So I have solved the problem forever? No. This is just a heuristic. It is a principled heuristic, with even some probabilistic considerations behind, but it's just a heuristic, and it can do very bad. I mean, in practice, it can work. A refinement of this heuristic is actually working. This is the basic heuristic, but this is not the heuristic that is used in practice. The one that is used in practice is a bit more robust. We'll see it next time. But this heuristic itself can fail because there are a number of possibilities. Consider the simple case of two clusters now. Let's say that I was so good, I was so lucky that I selected the centers of these two clusters. Okay, I was so lucky. Let's say that the number of leaders, let's call it L, is equal to 2. And then I want to return the top k elements, the top k documents for a query, and k is equal to 2 documents. Okay? Now, this is my query. Okay? What is the closest? Well, the closest centroid in this case is not easy. I took the wrong example. Okay. Yeah, a little bit further. Okay. So these are my 2 clusters. Okay? If you look at the geometry, if these are the leaders, this is the way the points are going to be clustered. Now, let's say my query is here, right in the middle. The closest centroid is this one. So the closest elements, so the top k elements I'm going to return are probably this and this. But actually, this is not among the top k documents for this query, because actually this is closer, right? So I'm making a mistake. Is it a dramatic mistake? As you see from the picture, probably not. But still, it shows a simple case and practical case in which I'm returning probably a set of k good results for the query, but not the best. Okay? So in general, these approaches, you cannot prove, as you have always done, worst case analysis. You see, worst case. So if you have clustering, forget about worst case. If you look at worst case analysis, any heuristic I can come up with is just to throw away. It will fail miserably. I don't know of any single heuristic that has provable performance in worst case scenarios. I know of a number of heuristics that can perform well under mild probabilistic assumptions. Okay, so clustering is not for worst case analysis. There is thing that works in practice. And we try to understand why, or we try to design heuristic that will make it work in practice. Huh? Okay? Which means proving that probably it works. Okay? So this is the basic idea. If there is no geometry, which means it's flat, every point is uniform, you can pick your square root of n candidates, leaders. You will do, let's say, you will do less work, because of course you are computing cosine similarities only against square root of n points instead of n. But in terms of accuracy, I don't know. Okay? I'll stop here, I think. We are all exhausted at this point. Okay, see you Thursday.